Imagine this. Your e-commerce site is getting flooded with customer queries from a location which is under severe cyclone warning. A customer types, I ordered a laptop. The delivery is in transit. There's a cyclone warning. Will it reach before Monday? Your expensive RAG system responds, our standard delivery time is 3 to 5 business days. For more information, please check our shipping policy. Technically correct, completely useless. Your RAG found the shipping policy, it retrieved the FAQ, it even cited the sources properly, but it couldn't connect the dots. Like estimating the exact delivery time by checking the weather, which could help. Meanwhile, your competitor's bot, it says your order will be delayed due to cyclone until Tuesday. Would you like to upgrade to air shipping for Monday delivery? I can process that now for 500 rupees extra. That's the difference between retrieval and intelligence. One is about finding information and the other is about completing the task. Hi, I'm Akshay, a senior machine learning engineer at PayPal, and I've spent the last 5 years watching companies burn millions on AI that can't actually do anything useful. I debug chatbots at 3 a.m. I've explained to leaders why their revolutionary AI can't handle a simple refund. And I've learned what actually works. Today, in this NIAT masterclass, we are going to fix this problem once and for all. We are building Agentic RAG, grounded task-solving agents that can plan, act, and cite. An AI that doesn't just retrieve answers, it gets things done. Think of it this way. RAG is like having the world's best encyclopedia. Agentic RAG is like having the world's best assistant. One tells you how to cook, the other actually makes you dinner. By the end of this session, you'll know how to transform your retrieval systems into an intelligent agent, build guardrails so that your AI doesn't go rogue and delete your database, deploy to production without burning through your AWS credits, and debug when things inevitably go sideways at 2 a.m. But here's my promise. No philosophical debates about AGI, no hand-waving about emergence, just practical engineering that ships on Monday. Let's build something real. Last month, a friend called me. His company had spent 6 months building the perfect RAG system. They indexed every document, tuned every embedding, optimized every query. The demos were flawless. Launch day comes. The first real customer asks, cancel my subscription and refund the last charge. The bot responds beautifully about their cancellation policy, explains the refund process in detail, even provides the correct form number. But can it actually cancel anything? Can it process the refund? Can it even send an email confirmation? Nope, nada, nothing. It's like hiring someone with a photographic memory who's never touched a computer. They can recite your entire operations manual, but can't actually operate anything. Here's the thing about RAG. And don't get me wrong, RAG is amazing, but it's fundamentally a librarian, not an operator. Think about these scenarios. What's your return policy? RAG handles this perfectly. Process my return. RAG is useless here. How do I reset my password? RAG's got you. And when you ask, reset my password, RAG can't help. See the pattern? RAG is great at what and how questions. It fails at do this commands. But here's where it gets worse. Sometimes RAG thinks it can do things. I call these hallucinations of capability. Here's the real example from production. A customer asks, transfer $1,000 from my savings to checking. RAG bot says, I've successfully transferred $1,000 from your savings to a checking account. Your new balance is. Plot twist. There's no integration with the banking system. The bot just made up the entire transaction. The customer checks their account. Nothing happened. Trust destroyed. So what makes Agentic RAG different? Instead of retrieving information, it plans. To process this return, I need to verify the order, check eligibility, calculate the refund, and update inventory. It acts, actually calls APIs, updates databases, sends emails. It verifies, checks if action succeeded before claiming victory. And it adapts. If plan A fails, tries plan B, and so on. It's like the difference between a search engine and a chatbot assistant. One finds the links about ordering pizza, the other actually orders your pizza. Now you might be thinking, that sounds dangerous. What if it orders 100 pizzas? Great question. That's exactly why we need some control surfaces. Let me show you what I mean. All right, let's pop the hood and see how this actually works. Imagine you're building a robot assistant, not a chatbot, an actual assistant that can do things. What do you need? First, a brain that can plan. Not just respond to keywords, but can actually think through problems. Version 1 of our agent just mapped intents to actions. When it's instructed to book a flight, it calls the booking API. Simple, right? But the real-world user says, book me a flight to Delhi tomorrow, but only if it's under 10K, and not too early because I hate mornings. Oh, and make sure it's a window seat. Our simple intent mapper just heard book flight and booked the first available flight. 6 a.m., middle seat, 15K. The customer was unhappy. That's when we added the planner, essentially giving our agent the ability to think before acting. It takes input from the user, the prompt. Book me a flight to Delhi tomorrow, but only if it's under 10K and not too early because I hate mornings. Oh, and make sure it's a window seat. Then it searches from flights to Delhi. It applies filter on the prices, shows some options to the user, gets the confirmation and proceeds with the booking. Second, you need tools, and I mean actual tools that do things. Think of tools like apps on your phone. Each one has a specific job. Calculator app is a math tool. Weather app, it has weather API tool. Banking app, it's a transactional tool. Email app is a notification tool. But here's the trick. Tools need to be strictly defined, no ambiguity. Here is an example of a bad tool. Send message to user somehow. This is how a good tool would do it. It should have a proper function name, proper parameters, and a proper return type. Why? Because when your agent is running at 2 a.m. and decides to send a message, you don't want it posting on Twitter when you meant email. Third, you need memory. There are two kinds actually. First, working memory like RAM. What are we thinking about right now? The current tasks at hand and recent tool outputs. Second, long-term memory like a hard drive. User preferences, past interactions, and learned patterns. If you don't integrate memory, you will end up in a similar situation to how once we had an agent with no memory limits. The user asked about their order. The agent retrieved their entire order history, all of it, 3 years worth. The context window exploded. The API call cost $12 for one query. Now we cap it. Recent orders in working memory, patterns in long term, smart retrieval when needed. Fourth, the control tower. This is what keeps your agent from going rogue. Think of it as a mission control for a space launch. It has step limits, maximum 10 actions per query, which is configurable, timeouts. No tools get more than 5 seconds. Guardrails. Can't delete data. Can't spend over X dollars. Can't message customers at 3 a.m. and kill switches. Emergency stops if things go wrong. And finally, the router. Not every question needs the nuclear option. It's like having both a Ferrari and a bicycle. You don't need the Ferrari to go to the corner store. If you have a simple FAQ, use a cheap model with basic RAG. For complex calculations, use better models with tools, and for sensitive operations, use the best model with human confirmation. This one optimization can cut your costs by 73%. Same quality, quarter of the price. This is how it works. A query comes in, the router decides complexity level. Planner creates action plan. Tools execute with guardrails. Memory stores important bits. Response goes out with citation. It's like a kitchen brigade. The head chef is the planner, decides the menu. The sous chef, the tools, do the prep. The expediter, control tower, checks everything. Waiter, the response generator, presents it to your customers. Before we add all these fancy agent capabilities, let's make sure our RAG foundation doesn't crumble. I see teams all the time adding agents, tools, and complex routing to a RAG system that can't even find the right documents. It's like putting a turbocharger on a car with flat tires. There are 3 pillars of RAG. Mess these up and nothing else matters. The first pillar, chunking, the art of breaking things. Here's a horror story. The company chunks their documentation every 500 tokens. Sounds reasonable, right? Their refund policy looks like this. Chunk 1. Products can be returned within 30 days. Chunk 2. Except for electronics, which have a 15-day policy. The customer asks about returning a laptop. RAG retrieves chunk 1, says 30 days. Customer returns laptop on day 20, gets rejected because retrieval pulls only the broader 30-day segment and delivers an incomplete answer. The customer acts on that information, returns the laptop on day 20, and the request gets rejected because the missing segment had the actual rule. Here are some better chunking strategies. Think of chunking like cutting a pizza. You just don't randomly hack it into pieces. You follow the natural lines. The first chunking strategy is semantic chunking, breaking at meaningful boundaries, not token counts. Second one is hierarchical chunking. Chunk the documents at chapter, section, paragraph, or detail. Third is overlapping windows. It's like reading with your finger, always keeping the context. My thumb rule is, if you can't understand a chunk in isolation, neither can your AI. Let's move on to second pillar. Hybrid search. It's the best of both worlds. Dense embeddings are like your intuitive friend who gets the vibe of what you're asking. BM25 is like your literal friend who needs the exact words. Let's say the user asks, what's the SLA for P1 issues? Dense searches think this is about response times, urgency, or support levels. But BM25 thinks find documents containing SLA and P1. Alone, each might miss the mark. Together, perfect results. It's like having both GPS and a local guide. GPS gets you close, local knowledge gets you exactly there. Now let's get to the third pillar, the re-ranker. It's like a bouncer at a club. Let me explain why. Retrieval gets you 20 possible chunks, but send all 20 to your LLM. That's like inviting everyone from the street to your party. The re-ranker is your bouncer. Looks at each chunk and decides who's actually relevant. Lets only the VIPs through. Now that we have a solid understanding of RAG, it's time to build one. In this lab, we'll build a basic RAG system for e-commerce customer support. We'll cover document chunking, embedding generation, FAISS vector indexing, retrieval pipeline, response generation, and limitations. That is, why is basic RAG not enough? Let's have a look. So, in this code, I have attached a setup environment.ipynb file, which is the basic environment setup notebook, which you can run to install all the necessary packages. The first section contains the imports. So as we have already installed all the dependencies in the previous notebook, you need not run any of these installations. Now getting started with the first notebook, you need to run a pip install FAISS, which we hadn't installed in the previous setup notebook. The next session is about importing the libraries and setting up your OpenAI client. We will be using GPT models to build our RAG and agents around. So as you can see, the setup is complete here. Now, let's move on to our knowledge base. So in order to build a RAG, we need to have a knowledge base which contains the documents which we'll be parsing to our AI model. So here I have built a sample knowledge base in text. You could in turn use a vector DB or a file itself or a markdown file itself as an alternative. So this is a knowledge base which contains a return policy documentation. So after running the cell, you will be able to see you have added 3 knowledge base documents. One is about return policy, one is about shipping policy, and then the other is about product info. You can glance through this text to get a better understanding of what your use case is going to be. Now let's get on to the next section of building our fundamental RAG. It's document chunking. So chunking, as I explained earlier, is a very important step when it comes to building a RAG. So why do we do chunking? It gives us a better semantic matching. Like it needs to fit within the LLM context window, and it gives more precise citations. So here I have created 5 chunks of this whole document with this lines of code. Now onto the next step, we need to generate vector embeddings. So here I'm using text embedding 3 large model to create embeddings, and this is also under OpenAI. So why do we need to generate embeddings? In RAG, when you are searching for a context, how it works is that when user enters a query, it is also converted to vector embeddings. So right now you have a data set or like a list of markdown files which contains the data in embedded format. How we do the retrieval part is that like we'll match the user query along with the vector DB. So we are going to embed the text. So we are using text embedding 3 large model, which is also under OpenAI. So why we need to convert this text into embeddings? So we have our source database which contains all our information. We convert this into vector embeddings. We often store it in vector DB, but since I'm using a small data set for example, we can have it in storage itself. So when a user query comes in, we also convert this into vector embeddings. And how we match the top closest embeddings which are relevant to our query is by doing an embedding matching. So it's often the cosine similarity between the user query embedding with the document embeddings which we have created. So this cell will create embeddings for all the chunks. Now I'm going to build FASS index for the similarity search. So as I explained earlier, once we have the embeddings generated, we do a similarity search to understand which chunks the user query is more relevant to. So let's test with the test query, what is your return policy? So while running this query, as you can see, they have converted this user query into an embedding here. So let's run this part. So what we are doing here is essentially, we are converting the user query also into an embedding so that we can do an embedding matching with the embedded data that we already have. So here we have retrieved the top 3 results. So the question that we have asked here is, what is your return policy? So the top 3 results that have been extracted are 1, the return policy.md, which is very accurate, and it has a score of 0.544. Within that, it has extracted the chunk which contains return policy, which is pretty relevant to our use case. And the other 2 documents are less relevant, hence the score is lesser. So now that we have retrieved the relevant chunks to our user query, we need to convert this into actual text which the user will understand. So we are generating the response part. So this is the generation part of RAG. So let me just run this. So let's see. I've created a function which will do the whole process end to end. So let's just demo it with a sample query, which is, what is your return policy? So it's retrieving the relevant context and it's generating the answer based on it. So as you can see here, our return policy allows items to be returned within 30 days, which is the same as what we had fed in. So that is pretty accurate. So let's ask another question which is already there in our document. How long does the shipping take? So again, the whole process, it's creating the embeddings, it's doing a cosine similarity on it, and then retrieving the chunks and generating the response. So yeah, this is pretty accurate. Shipping takes 5 to 7 business days, which was the same as what we had given in the document. And again, another question which is relevant. So you can try running this and understand how these are retrieved. So yeah, these are working. Now let's try to understand the limitations of a traditional RAG system. Here I have a query. I want to return order hash 12345 because it arrived damaged. Can you process this? So what it does is that it went through the documents. It found the top matching document, which will be obviously the return policy. As you can see, the score is pretty high. And it just returned, yes, you can return order 12345 because it arrived damaged and you are eligible for a full refund. Please submit your return request. So with this, they have just cited what you can do. But the user query was, can you process this? The traditional RAG is unable to do that. So yeah, this is the limitation which we have identified with the baseline RAG. Now, this is where Agentic RAG comes in. Let's get on to the next lab and understand how to fix this. In this lab, we have built a document chunking, embedding generation, FASS vector index, and a retrieval pipeline. We have also shown how to generate response, and we have seen what worked. For example, simple policy questions, information retrieval, and accurate answer from knowledge base. Also, we have identified basic RAG that can process action-oriented requests, data verification, multi-step tasks, and can't fetch real-time information. And that's where Agentic RAG comes into picture. It can solve these limitations. Now for the fun part. Let's give our RAG a brain upgrade. Remember that complex delivery question that stumped our RAG? Let's watch how an agent handles it. The query was, order placed Friday 7:40 p.m. Mumbai to Delhi during Diwali. When exactly will it arrive? RAG's pathetic attempt was, orders typically take 3 to 5 business days. But here's how an agent thinks. Let me think this through. 7:40 p.m. is after cutoff. So let's process the next business day. Next day is Saturday. Okay, so let's wait for Monday. Check the calendar. Oh, Monday is Diwali, the holiday. So Tuesday, the processing starts. Mumbai to Delhi, 2 to 3 days normally. But wait, checking the weather, there's a cyclone warning. Add 1 day of weather delay. Final answer was Thursday by 6 p.m. and the confidence was 85%. See the difference? The agent isn't just retrieving facts, it's reasoning through the problem. The secret sauce behind this are the planning strategies. First is the react pattern. Think, act, observe, and repeat. Perfect for exploratory tasks, like cooking without a recipe. Taste, adjust, taste again. The user asks, find me the cheapest flight with good reviews. This is how the agent behaves. First, think. Need to search flights. Act. Query the flight API. Observe. Found 10 options. Agent thinks again. Now it needs reviews. Acts. Checks the reviews API. Observes. 3 have good reviews. Later, it thinks again. Compare the prices and then finally it gives the results. Here is your best option. Second, plan and execute. Make the full plan and then execute the steps. Perfect for well-defined tasks. It's like following IKEA's instructions. All steps are planned up front. The user asks, transfer money from savings to checking. The agent verifies the identity, checks account balances, validates the transfer amount, executes the transfer, and sends confirmation once the transaction is done. The third is tool orchestration, the art of delegation. Your agent is like a conductor. It doesn't play every instrument. It coordinates them. Fourth, the sequential pattern. Here's the step-by-step. It checks inventory, it reserves an item, processes the payment, and ships the order. Each step needs the previous one. It's like a factory assembly line. Now for fifth, parallel pattern, all at once. Simultaneously, it checks the weather in Mumbai, it checks the weather in Delhi, gets the holiday calendar, and fetches shipping routes. It's like a pit crew changing tires. Everyone works simultaneously and seamlessly. Sixth, and my personal favorite, the circuit breaker pattern. If a tool fails twice, stop trying and switch to fallback. Saved us once when a weather API went down. The agent kept trying to check the weather. After 2 failures, it switched to using historical average. The customer never knew. Finally, the self-critique loop, which is the paranoid android. Before responding, the agent asks itself, did I actually answer the question? Is my answer grounded in facts? Am I confident enough? And should I double-check anything? This one feature eliminates 90% of hallucinations. It's like having a fact checker built into your brain. Let's say the agent is about to tell the customer their package was delivered. The self-critic kicks in. It says, wait, I'm citing tracking info from a different order number. Caught the error, fetch the correct info. Crisis averted. It's time to evolve our RAG into a proper agent. Do you remember that complex query that broke our RAG? Now we're going to solve it properly. What we are adding? A planning brain that decomposes complex queries. We'll also add a tool suite which contains holiday checker, weather API, business day calculator. We'll also add state management to track progress and a self-critic for verification. So here is what we are going to build in this lab. Tool definitions, order API, refund calculator, and returns processor. We'll use LangGraph to build agent state management. We'll create a React planning loop. We'll add citations to track every fact. And we'll also add multi-step task solving. So let's go ahead with the lab. So let's run a pip install to install LangGraph, LangChain, and the dependent modules. Here we are importing all the necessary libraries and also setting up our OpenAI client. And the keys have already been set up in the setup lab, so we don't need to think about it. So here I've created a mock order database which contains order ID, customer email, and other relevant information. In production, there will be a real database, but for this demo, we'll use a sample dictionary. This dictionary contains a couple of orders along with the order ID, customer email, and other relevant items such as the items that we have been ordering. So yeah, after running this cell, we've gotten like a couple of orders that we have added in the database. So now let's go ahead with the tool definitions. As you know, for Agentic AI, you need to have a few tools, as we have mentioned previously, which will do its specific task. So here, the tools I'm adding are 1, the check order status, which will return the order status of a particular order. Second would be the calculate refund, which will be calculating the refund on a particular order. Third is process return, which will kind of initiate a return based on the user query. As you can see, we have order ID as one of the mandatory parameters in all of these use cases. Coming to tool 4, now this is a simplified version of the retrieve policy. So we already had the RAG in place, so instead of not having it repeated here, I've added a simple function which will return the return policy as well as the shipping policy. So here, as I'll execute this, you can see if you ask what is the return policy, it will simply return the actual return policy. So this was extracted from the knowledge base, but yeah, instead of having the whole RAG set up here, I've just added this function for ease. You could alternatively have the whole RAG set up here, try it on your own. Now, coming to the next section, and one of the most important sections here. So we need to have tool registry set up for OpenAI. So OpenAI has a feature called function calling, which we'll be leveraging to kind of generate the output in a structured response containing the function name and the necessary parameters, which we will be needing to run the particular functions. So yeah, here, as you can see, these are the functions. So what we are doing here is we are simply defining what all tools will be made available to us. So we need to let OpenAI know that these are the tools which are available upon your discretion. So here, one function is check order status, which I had earlier defined. Similarly, for calculate refund, there is process return, and retrieve policy, which I just explained previously. So yeah, I'm just creating a tool map which contains all these policies. So yeah, this will create a tool map which contains all the function infos. Okay. Now let's move on to the next stage, which is nothing but the agent state. So we are using LangGraph to define the agent states. So let me just quickly run this. So as you can see, the agent state has been defined, and these are the states: query, message, tool results, source, steps, and we also have defined the max steps. So max steps we have put as 10 in order to not exceed that limit. Like, it shouldn't go for more than 10 steps, then the queries become even more complex. Okay. Now let's get on to the agent nodes. So as we have defined in the theory part, there are 3 key nodes here. One would be the planner, which will decide what to do next. Then as in like what tools to call as well. Then we have tool executor, which will run the particular tool for that use case, and responder, which will generate the final answer. So let me just define planner, which is node 1. And next in this cell, we'll define the tool executor. And in the third cell, we'll define the responder, which will generate the final answer along with the citations. Now, you might have remembered, we have defined what control flow is. So here we'll create the control flow, which will decide like whether to use the tools or like generate final response or like what the next step is. Okay. So as you can see here, we also had defined max steps as one of the variables. As you can see here, you can note that if you can take a look at this, you can see that we had defined max steps as 10, as I had explained previously. So if the number of state steps increase beyond 10, we will stop and then return the response. So control flow will decide whether we have to call further tools or just generate response. So here, as you can see, we had previously defined the max steps, which was 10. So if the number of steps exceed that, we will push the system to go to the response state. Okay, so let's build the agent graph by assembling everything into the LangGraph state machine. So as you can see, the agent graph was built. And as you know, the flow will be planner, tools, and then planner or tools, and so on, depending on the control flow, till we get the final response, and it calls the responder, ending the flow. So here are a few helper functions which will kind of help us run the queries. So let's start with a simple question. Where is my order? Like so and so. So it goes to the first step, which is planning. So it identifies the function to be called is check order status. And it goes and checks that particular order IDs or status, and it retrieves it. Then it goes again to the planning step, and it generates the final response, which along with the citations. So as you can see, it only took 2 steps and 1 tool was used, and you already have successfully retrieved the order status for your order 1, 2, 3, 4, 5, which was the same as what we had given in the JSON. So as you can see, you have the correct delivery date for this particular order, and this was not just a knowledge-based kind of thing. It has done what a function would do. So we have called a function which was connected to a JSON in this case, but ideally there will be a DB which contains your company's live order status. So it will be calling that. You can go through this markdown in order to get a better understanding. I've added some text for you to understand it well. Now let's go run another query. What does this query say? I want to return order 1, 2, 3, 4, 5 because it arrived damaged. Can you process this? So upon running this, first, as it goes to the planning stage, and it checks the order status. Yeah. And second, it identifies, so like from this context, it identifies that we need to calculate the refund, like how much amount has been returned to the user. So for that particular order ID, it calculates the amount of refund that needs to be given, like whether it's eligible for refund or not. And then it generates the final response with citations. So as you can see, your order ID, and it has even given the details of the order, was delivered on Jan 15, 2025. The source was from the order API, and you reported that your item that you received was damaged, so it's eligible for a full refund. This has been fetched as per the refund policy, and if we confirm, it will go ahead with the refund processing, because we already have added a capability which will initiate the refund as well and the cancellation. So as you can see, this involved multiple steps, as in 3 steps to be taken, and it also involved multiple tools to be used. It wasn't a single tool kind of query. Now you have checked and you have understood like the agent part is working. So let's take back to the fundamentals and check if like the RAG part is working or not. And let's send a query, like what is the return policy here. So as you can see, it has returned the actual answer and it's working. Right. So now let's get on to an edge case, right? Let's check the status of an order which is not there in the list of orders that we had given. So it runs, but yeah, as you can see in this output, it says, it seems order 9999 could not be found in our system. So that means it has executed the tool and it has checked all the order IDs there, and it couldn't find this particular order ID. So it's working well. So it's gracefully handling all the errors. For our final test, let's try a complex multi-request. So this contains details about 2 orders. 1, I received order so-and-so in damaged state, I want a refund. Second, also, when will the order so-and-so will arrive? So upon execution, as you can see, it is executing 3 tools. So it was able to segregate the different functions, and where parallel processing is needed, it was able to parallelly call these tools. And as you can see, within 1 iteration, you have extracted all the results. So you are able to get the answer. So for the first order, it says it was delivered on this date and it was damaged and you are eligible for a full refund. And for the second order, it says it's currently in transit and has not been delivered. And it even says the tracking ID, which was there again in the DB. So yeah, it solves a complex problem. So it was able to handle a multi-request request. So it handled 2 separate requests in 1 query. So now you can try on your own. When you run the same query, like Friday evening, Mumbai to Delhi during Diwali, your agent will recognize it needs multiple steps. It will call tools in that smart order. It will combine the information correctly, and it will give a specific, accurate answer with reasons. So what have you learned in this lab? Tools aren't scary. They just function with rules. Planning doesn't need to be complex. Start simple. Self-critique catches most errors. And logs are your best friends for debugging. With this, you will be able to attain user satisfaction. Finally, actual answers, they'll say. The cost might be slightly high, but it's worth every penny. Let me tell you about the day our agent went into production. Development, it worked perfectly. Staging, smooth as butter. Production day 1, 47 errors in the first hour. These production issues were identified. The first issue, the cache catastrophe. Our agent made the same weather API calls 2,847 times in 1 hour. Same city, same date. Our bill, impressive. What's the solution? It's semantic caching. If you have answered weather in Mumbai tomorrow in the last hour, just return the cached results. The weather doesn't change that fast. The results, 70% cache hit rate, 70% cost reduction. Issue number 2, the timeout error. Agent tries to help the user. It calls the slow API. It waits, and then it keeps waiting. The user gives up. The agent is still waiting. It's like a dog waiting for its owner who had already left. What's the solution? Aggressive timeouts with fallbacks. If the tool doesn't respond in 3 seconds, move on. Have backup plans for every external dependency. Send the response like, I'm having trouble checking the live weather, but based on seasonal patterns, and then give out the seasonal patterns. Issue number 3, the context window explosion. A user with 3-year history asks about their usual order. The agent retrieves everything. 3 years of order. Context window explodes. API rejects the request. The user gets nothing. What's the solution? Smart context management. Show recent items in detail, older items as summaries, and retrieve more only if specifically needed. Here are some more approaches that will make your agentic application production ready. The router revolution. Not every question needs GPT-4 or 5. It's like using a Ferrari for grocery shopping. Your routing logic should look like this. If the user asks, what are your hours? You can use GPT 3.5 Turbo, which is cheap. If the user asks, calculate my tax refund, use GPT-4, which is smart. If they ask, delete my account, use GPT-4 with human confirmation. You have to be very careful. This is one change which will cut costs by 73% with zero quality impact. Next is the monitoring stack. You can't fix what you can't see. Our dashboards track latency per component, where are we going slow, tool success rates, what's failing, cost per query type, what's expensive, and user satisfaction by feature, what actually matters. And now, graceful degradation. When things break, and they will, it should fail gracefully. Is the tool down? Then use cached or estimated data. Is the model overloaded? Route to simpler model. Is everything on fire? Just return, I'm experiencing issues. Here's a human. It's like having a backup generator. You hope you never need it. But it's better to have and not want it than to want and not have it. Now that we understand what issues can arise in production, let's see how we can avoid them in the next hands-on lab. In parts 1 and 2, we built 2 key systems. A baseline RAG, which handles simple retrieval and generation, and an agentic RAG, which added planning, tool use, and proper citation. But taking these systems into production requires a lot more. Real-world deployments need strong cost control through caching and strategic use of cheap models, as well as high performance with parallel execution and low latency optimizations. They also demand solid observability, including metrics, logging, and tracing, along with robust safety features such as guardrails, PII protection, and validation. And of course, none of it is useful without a reliable deployment. An API wrapper that can scale, monitor, and handle real traffic. In this lab, we'll build exactly those missing pieces. You'll implement a caching layer that supports both semantic and exact match caching, add observability with detailed metrics and tracing, integrate safety guardrails like PII masking, cost limits, and validation, and wrap up everything in a production-ready API using Fast API. Let's get on with the lab. So the first cell here is regarding the notebook setup. We are importing all the necessary libraries and setting up our OpenAI as well as HTTP client. So as you can see, the environment variables have been loaded. So let's get to the first section. It's the caching layer. So initially, for embedding calling, as you can see, each embedding calling is requiring close to 1/100th of a cent. Each LLM call costs from 1 to 10 cents. Let's tackle this and reduce costs by using cache at multiple levels. So we'll be implementing exact match cache, which will identify identical queries, which is a hash-based mapping, and semantic cache, which uses similar queries, which will be based on embedded base mapping. And we'll also use tool result cache, which will prevent repeated API call, like the weather scenario we had mentioned earlier. So here we have enabled semantic cache. Now let's do a little bit of testing. Right. So here we have asked the question, where is my order ID? So in this case, it will do an LLM call, and then for the first query, it will generate that particular answer. So in this scenario, there is no pre-existing cache. So as you can see, there is no cache here. But if you repeat the same question or a similar question, which is like, where is my order, and you get the same answer, what you will get is you will get a cache hit, and instead of calling the LLM, it will retrieve from the previous. So in this first case, when I asked the normal order question, it did not have any prior cache, so it did not hit anything, and as you can see, it returned none. The LLM call was made and you got the answer. So when we ask the same question again, or a similar question again, where is my order 1, 2, 3, 4, it was able to catch the cache and thereby saving $0.05. So here you can see the cache statistics, how many hits and how many misses, and how much amount was saved. So now let's move on to the observability metrics. So here we are trying to identify what the latency is, what the cost is, and the quality. So we'll also try to identify any failed tool calls or any rate limits that were caught and resulted in calls getting failed. So we have initialized the metric tracker. Now let's get on to the safety guardrails. Some of the functionality that we are trying to capture here is to prevent infinite loops, which will increase our cost by a lot. We'll also check if private information is getting leaked, which is causing compliance violations. We'll also check if there are any hallucinations or API abuse, like rate limiting. There might be some attackers who might overload our API with thousands of queries purely to attack us. These guardrails prevent that. So these guardrails have been implemented. We can test some of it out. So here we have added a query which includes our social security number. So ideally the query would have gone like, my social security number is this, and my email is this, and the card number is this. So we have added a mask here which has essentially masked the social security number, the email, as well as the card number. So this was also able to validate the citations. Now let's put it all together, the caching, the metrics, as well as the guardrails, to make our production ready agent. You can execute this cell for that. This production ready agent query will take a query from the user, and it already has the production ready features inbuilt into this function. So let's try a live demo. In a previous order, we had done for the same order ID, because of which we got a cache hit. And instead of going to the LLM or doing any retrievals, it simply returned the same answer. Now, production ready agent query for... Okay, now let's run it again. And as you can see, it's working successfully and it's saving 5 cents each time. So let's try a different query, which is, what's the status of my order 1, 2, 3, 4, 5. As you can see, you are able to get the final response along with the citations. So in this case, we are running not the exact sentence, but we are asking what's the status of order 1, 2, 3, 4, 5. So here, what I'm running is what's the status of order 1, 2, 3, 4, 5, which is kind of different from the previous question. So here, what we are doing only is the check order status, and then we are returning the exact order date, shipping date, and all those information. But the order status which was previously fetched has already been extracted, so thereby saving that amount. So here we are trying to get the return. So now we are running an entirely new query. So it was successful and it extracted all the info. And now that I ran it a second time, since it was a cache hit on exact, it saved me so and so amount. So let's take a look at the metrics dashboard of all the queries so far. So I was able to generate all the information here. So the average latency is 6 seconds, which takes for multiple queries, and the average cost is around $0.012. And it also even tracks how many cache hits happened. Now let's get on to the last part, which is deploying a fast API. So we can't simply put a notebook to production, which is why we have to build an API. So here we are using fast API to do the same. And this cell will create a fast API with the necessary endpoints, which will be deployed locally, which you can maybe Dockerize it and deploy it to your production server. Now let's do a cost analysis. So here we are getting a detailed cost analysis for a number of queries per day, like based on current cache hit percentage. It calculates how much amount we could save and all the detailed info. So these are some of the important stuff that you need to have while shipping all this to production. Let's understand what the key takeaways here are. In this module, we turned our Agentic RAG system into a production-ready service. We added a caching layer, exact match, semantic cache, TTL, hit rate tracking, and we built observability, latency, cost citations, and traces. Implemented safety guardrails such as step and cost limits, PII masking, citation validation, and wrapped everything in a fast API, production API with health checks. We also added metrics and error handling. To take this system into deployment, the next steps are very straightforward. You can use Redis and rate limiting for scaling, add OpenTelemetry and Prometheus for monitoring, and evaluate quality with Ragas and A/B testing, and continue the cost optimization with cheaper models. You can also try batching and streaming. Then you will have successfully created a production-ready Agentic RAG system. Congratulations! Let's take a step back and look at what we have built. You had a retrieval system that could find information but couldn't do anything about it. It was like having a phone book but no phone. But now you have an intelligent agent that can plan multi-step solutions, uses tools responsibly, cites solutions accurately, handles failures gracefully, and it runs efficiently in production. It actually helps real users. We started with a broken RAG that couldn't handle complexity, added planning brain for intelligent reasoning, integrated some tools for real-world action, built guardrails for safety and control, optimized for cost and performance, and hardened for production reality. What's the real impact it can make? Last week, a team using this approach told me their metrics. The support ticket escalation dropped by 67%, and the average resolution time went from 12 minutes to 2 minutes. The customer satisfaction increased from 3.2 to 4.6 stars, and their monthly savings was 4.2 lakhs in support costs. But my favorite metric, their lead engineer sleeps through the night now. No more 3 a.m. pages about the chat system. Do you want to make a similar impact? These should be your next steps. Start small. Pick one use case. Order tracking, FAQ, appointment booking, whichever you want, and then nail it. Measure everything. Before you add agents, know your baseline. You can't improve what you don't measure. Build incrementally. Better RAG, add planning, integrate first tool, add monitoring, and then scale up. Share your wins. Build something cool, hit a weird bug, found a clever optimization, share it. The community needs real stories, not Medium articles about AGI. Building agents isn't about making AI smarter. It's about making AI useful. Your users don't care about your embedding dimensions or transformer architecture. They care about getting their refund processed, their flight booked, or their questions answered correctly. So focus on that. Build agents that do real things for real people. The rest is just implementation details. Here's my challenge to you. Take the worst, most painful support query your company gets. The one that takes 5 back and forth emails to resolve. Build an agent that handles it in one shot. And when you do, share it and tag me. Show the real world what practical AI actually looks like. Because we have enough chatbots. What we need are agents that work. Let's keep building.